I think it's a relatively new design of downconverter, at least in the amateur world. It's probably nothing clever, but I've not seen it done this way before. So I'll talk about the concept of this converter. The key part of it is a voltage tunable filter. I'll spend a bit of time talking about that. Also the VCO, phase lock loop, complete downconverter then, and some performance results, which I'm highly embarrassed about because there are noise figures in there quoted to 1/100th of a dB. I feel well rebuked and will never do it again. So the problem, different regions of the world on 13 have got different frequency allocations. And if you want to be, particularly with septum feeds now, where you have a chance of reasonable circularity over the band, you would like to be able to receive all of them and participate. However, 4 frequencies is a bit of a problem. And present solutions people have found is either multiple downconverters, different IFs using 26 megs or 28 to go from Australia to the States or whatever. And in my view, that's a bit messy. And under the stress of EME operation, you're likely to forget which receiver you're on and probably just listen to the wrong frequency. Plus trying to cope with people who are transmitting on the distant stations frequencies as well, rather than sticking to their own local transmit frequency. This is a bit of a nightmare. We even found that on 10 gigs when working our colleagues in Japan. We'd find half of Europe up on 10450, and it just got complicated. So this is to try and make it easier. So here's the design concept of the downconverter. It's a conventional 144 IF, 13 SEMS in. It's a complete downconverter with a reasonable noise figure. The key to it really is the use of a synthesized local oscillator, which you can set with 2 bits to any one of 4 LO frequencies. So when the synthesizer produces its control voltage to lock the VCO, we use the same control voltage to tune this filter. So this effectively gives you the image rejection is tracking across the whole of the band. And you could use the downconverter anywhere in the band by programming the synthesizer. If you want to have one of the frequencies as 2401 for amateur satellite, you could do that too. Or use more bits in the synthesizer and have as many frequencies as you want. So the first filter is wide. It's deliberately wide to cover the whole of the 2.3 to 2.45 band. Image rejection, of course, is very poor with that because it's a wide filter. So if you're at the top end of the band, you're almost overlapping the filter response. So you'll only have 4 or 5 dBs of image rejection. And that's the job of this filter, to do the image rejection for you. Fairly conventional mixer, IF gain block, and that completes the design. So moving on to the tunable bandpass filter, which is used twice in the design. So excuse me if I spend a little bit of time on how it works. It's based on coupled microstrip filter. I've used these kind of filters in a number of projects over the years, and it's basically just grounded, nearly quarter wave lines a certain distance apart, and the RF is tapped in on at the appropriate distance to get the impedance match. Frequency bandwidth is basically set by how closely you space the lines, and the resonant length sets the frequency. So if you want a wideband filter, you just push these guys together, changes the impedance match, so you move the taps around a bit. And it's a very simple, easy filter to print. And for up to certainly 13 SEMS and maybe 9, has enough image rejection with a 144 IF if you match it to for just narrow band. So that was the start. I've done these filters for a long time. So the trick was to make it tunable. And I looked at a number of designs of how to do this, and eventually settled on putting varactor diodes inside the filter length. If you put them on the end and try and tune it, then the off capacitance is just far too high, and it pulls the frequency response of the filter far too down low, is more lossy, and it's what TV tuners do, but in this case wasn't going to work well enough. So I found the best compromise was to put the diodes inside the filter. The grounding of the filter here provides the ground for the varicaps, and then you just feed the tuning voltages in at the tapping point of the varactor and the line. So if you think about it, the filter really, the resonant frequency, if the varactors are a short, so if there's low voltage, the diodes are shorted, then the active length of the filter is all of that. And as you decrease the capacitance of the diode by turning the tuning voltage more positive, then effectively the filter becomes shorter, and that's how it's tuned. So that's the basis of it. The trick really was to get the right the right degree of tuning to match the oscillator, so that you get tracking between the imagery filter and the local oscillator frequency. So some experimentation took place to find the best position of the diodes. If they're down here, you get more tuning range, but the losses are high, and so it's a question of finding the right point to insert the diode. And that was, at the time, done experimentally. I've since discovered how you can do this by design. And I'll hopefully have time to talk a little bit about that as we move on. So this shows you what that filter looks like in 3 dimensions. This is actually a printout from what is my favorite piece of software at the moment. We talked about yesterday, Sonnet. And you can see the input line here, tap, grounding of the thing is done through anybody who's ever built one of the kits will know these little pins. We still can buy those, fortunately, and that will ground the ends of the line. And in the modeling, actually, this software can get the inductance of this quite accurately and tell you where to tap the line and get the thing properly matched. Otherwise, it's a bit of experimenting, but doesn't take too terribly long. So that's the basis of it. And then in this modeling, I was able to, with Sonnet, cut the lines here, put ports in, and then you can export all of the parameters of this into the software again and put varactor diodes in to look at how the thing tunes. So that's basically how the modeling works. But when I designed this, I didn't know anything about Sonnet, so it was all done by hand. That's what it looks like, fairly horrendous photograph, but you can see it's upside down as well. You can see the RF lines come in here, decoupling capacitors, tap from the 50 ohm line onto the diode. Here's the grounding pins. Here are the diodes, the varactors, BB883, good old device for satellite TV tuners with a very low off capacitance. And 100K resistors mounted on these are 1206 size chips mounted on their side to minimize stray capacitance to ground so that it doesn't detune the filter to any great extent. And then this is just the end of the rest of the line, but it's got lots of solder on it because it's had tabs and cutting and scalpel blades and all the usual stuff to get the thing to work. So that's the heart of it. This is what gives you the image rejection, good image rejection at any frequency within the band. But here it is again in the VCO. So the VCO was thanks to S53MV for his paper on low phase noise oscillators. So this oscillator is running directly at the LO frequency, like 2160 megs. And it's a fairly conventional oscillator in that it's how we all learn how oscillators work. There's an amplifier, it has gain, there's a frequency selective network, in this case the tuned filter, and then you feed the output back to the input, and once that signal delay is a total of 360 degrees or multiples of 360, it oscillates. So it's really just an amplifier with feedback. And provided that this amplifier has enough gain to overcome the loss of the filter and the rest of the losses, it oscillates. It's terribly easy, and they really work well. I remember at the Martlesham Round Table, Andy, G3WDG, and T talking about, we need an oscillator to go with these mobile phone synthesizers. Well, this is the one I propose, because I've designed these now from like 1152 up to like 2.6 gigs for all of the equipment, from up to 24 gigs, and it really works quite well. So the phase addition is just shown here. From A to B through the amplifier, minus 41 degrees, minus 110 degrees phase shift through the filter when it's on its resonant frequency. I used a low-pass network here to put another 90 degrees in a small amount of space. And the remaining 119 degrees is just a length of transmission line to get the thing to oscillate. Tweaking them is just a question of getting the phase, tuning the filter. If you haven't got the phase right, it stops oscillating before you want it, so it might work over part of the band, and you can just add or take phase out until the oscillator tunes nicely over the wanted band. And then you just tap off a little bit of the output from the collector here, and that's some goes off to the synthesizer, the rest goes off into the mixer. So that's the LO, but it's using the same tuned filter arrangement as in the image filter. Again, sorry for the photograph, but this is this is it. There's the tuned filter part, looks the same as the other one. In the middle is the amplifier. Down up here, I think, is the 90-degree shunt C, series L shunt C network, and then these are the rest of the phase length. As you see, there's been a certain amount of tweaking, and the RF is just tapped off here from the collector line. So I talked about tracking as being very important. So as the vari-cap voltage is set by the synthesizer, you want to know that the image filter is being tuned to the correct frequency. So what this graph shows you is the vari-cap tuning voltage versus the response of the filter and also the oscillator covering the band. So as you see, the worst case error in here is probably about 10 or 15 megahertz. So because the image filter has got about 30 megs, 40 megs of bandwidth, the thing is always good enough on tune. Well, this took a little bit of playing with to get it to work, but I was quite pleased with the tracking accuracy at the end. Then talk a little bit about the synthesizer. I apologize, this part is sort of basically now obsolete. But as Andy was pointing out, you can find these in mobile phones and extract them and reuse them. There is also, I think, still in the paper I've given part number of a part that I think you can still buy that is an Analog Devices version of the same chip. So I think it's still available. This is thanks to V1ALQ. It's based on his design. And the only thing I had to add basically to it was a voltage amplifier op-amp with a gain of 2, because the LMX2326 has a maximum of 5 volts output to tune the variCap, but in order to get the filter to tune from the bottom of the band to the top, I needed nearly 10 volts. So we had to bump up the output. Slight noise penalty probably on the oscillator, but not too much. So this is basically a V1ALQ circuit with a few minor tweaks. And this is the PIC that drives the programming of the synthesizer and the 2 bits there that set the frequency. So you just have these low or high, and that will tune you to the any frequency. And you could obviously remote this easily just by switching those from the shack, but having this set at the dish if you wanted to have this remote. Lock indicator, LED. Somehow or other with this synthesizer, sometimes that will light, even though the part is not properly locked. So sort of beware somehow. There's different ways of setting the lock detection in the chip, which help that, but I've still seen them light on, but the synthesizer not completely locked. But once you've got the thing set up, it's always reliable. It's just during development phase or playing with the loop time constants or whatever that you come across that. The PIC I've chosen, I'll talk a little bit about in a moment, but what you can see is there are just 2 data inputs to the PIC for programming it. So there's a serial out and a serial in line that allow you to program the PIC. This is a learning experience for me because it's the first synthesizer I'd ever done. So I was quite. I think I approached it with some care. I've been trying to avoid synthesizers for years and stayed with crystal oscillator chains. But I think finally the concept of having a frequency when people hear you off the moon that's just a nice straight line on Spectran rather than doing this was the final push. I don't use GPS locking routinely in any of the equipment. I basically think it's a waste of time and expense. What works well for me is just a high-quality 10 meg brick that you can set to the right frequency from your single GPS DO. But from then on, you can leave that 10 meg brick in the equipment, take it out, and you'll always be within a few hertz, and you don't have to have everything locked in real time. Just a personal thing. So programming the PIC turned out to be very easy, as National Instruments and now TI have got, who took it over, I think, have got this Codeloader software that you can download free, put in the frequency you want, set up whether you want to have a 10 meg reference in, you set, and then I'm going to divide it by 10, so I've got 1 meg steps. Because for an application like this, you only need 1 meg steps because the frequencies are all nicely set at one. The bands or the sub-bands always are in 1 megahertz increments. So you set this up, run the program, and it gives you 21-bit codes that you have to then send to the PIC. 3 different registers you have to program. One of them sets up the divide ratio for the reference. One of them tells the PIC how to do lock detect and all the other things. It tells the synthesizer what kind of lock detect to put on. And the other one, the N register, here is the word that actually is the frequency that you want. So in this case, we've got 4 of those which you need to work out before you write the program to set the frequencies up. And it's relatively easy to modify if you want to change frequencies for something else. Sorry, this is turning into a synthesizer tutorial, and I'm boring everybody who knows how to do it. But for me, this was a bit of a learning curve. So the PIC I chose, again, being absolutely new to this and not knowing anything at all and relying totally on my son, who was doing this at school, was an educational level PIC called a pickaxe. and these are what the school children learn to do PIC program, at least in the UK. The beauty of this is they're A, very cheap, and B, you need no special interface. If you still have a conventional serial port on the PC, you can just connect it directly to the PIC. There's no PIC board or external stuff needed, and it's very simple to use. And we now have too much of the house with gadgets that have got these things in as a result of this. But anyway, but if you don't have a serial port, you can use this cable you can buy, and it's programmed in BASIC, which is what I first learned together with Fortran when I was younger. So the kind of code that you write, again, free download from the people who sell the PICs. It's all in BASIC, and really I only wanted to show you how easy it is to edit. You just need to change this for different frequencies once the code is there. And if anybody should ever want to try this, then happily let them have the code. And all the software does is it loads the 3 registers, and it sets the 2 registers that it never has to change. Then it checks the data pin status, and if you change any of the voltages on the 2 control lines, it then spits out another 21 bits to reload the register. That's what it looks like as a PC board. So we've got the synthesizer chip, the loader there with the 2 data inputs. The rest of it is just voltage regulators and 10 meg input. One thing I did do when developing the PLL is not knowing terribly much about phase noise and how it affects things, and not having any equipment to measure it. I did obviously aware that phase noise matters. And this was actually when using the synthesizer as the new 10 gig local oscillator. And what I found was when playing with the design program to do the loop filter, you can choose what looks to be fantastic in terms of performance in the program that does the design, using 4-stage networks, and the whole thing looks fantastic. Then you build it, and you find you get a nice, clean spectrum analyzer picture of the oscillator. It all looks great. And you put it onto the receiver and try and listen to something, and you can't hear anything. And this is just due to, I think, the phase noise of the oscillator. So what I did was found a weak signal and then compared the PLL local oscillator to a crystal and then played with the loop of the PLL until I got the same Spectran recovered audio signal to noise, because at the end of the day, that's all that matters for EME, is that you don't degrade the signal to noise, even if the noise bandwidth isn't brilliant. But for EME, you just don't want to degrade the audio, and that's, I found, worked quite well and works up as high as 24. So I think for this 13 SEM, the phase noise is going to be absolutely fine. The rest of the downconverter, fairly simple and boring. Seems hard to find MIR6s and so on these days, so I moved to some horrible tiny package that's very difficult to solder as the IF gain block. It starts off with the version of the DJ9BV preamp, which I've used a lot on 13. It's got plenty of bandwidth to cover the whole band. The wide image filter, the gain, second stage gain, the tunable filter that we've talked about, and then this mixer is just a scaled version of something we used on 10 gig a long time ago. Added a trap here. There's a quarter wave line which stops the 2.2 gig LO from blasting this IF amplifier, which has got lots of gain at at the LO frequency. So that improved the performance a bit. So this is what the downconverter looks like in its prototype form. Everything's now screened because there's too much interaction between the filters and you get oscillation with all the gain that's in there. So that's the LNA section, fixed image filter, IF gain block, tunable filter, mixer, IF amp, and the VCO. So that's all on one board. And on the other side, we've got the synthesizer on the ground plane side. So this is one of the standard Schubert boxes, which we've used a lot before. So here's the performance. What do we actually get? And as you see, the noise figures are pretty reasonable. Tolerance on those, I have no idea. Let's say plus or minus half a dB. So the noise figure is absolutely flat across the band. It's one of the advantages of having tolerances. And we've tested it at 2302, 2304, 2320, and 2424. Conversion gain measured on the noise figure meter. So that's probably 5 dB's error, so it's flat again. Shall we say it's around 40? It's enough. The image response, which I did measure properly with SIGGEN and Spectrum Analyzer, we're pulling nearly 40 dB of image rejection at all 4 frequencies. So I think, personally, that's plenty good enough. So those are the references. We've got the original VCO. We've got V1LQ synthesizer article. This is all about how to design the PLL. It's really PLL for dummies, which was great for me. Pickaxe, about the pick. The Codeloader software to program the synthesizer with. Versions of these loading software. And the original Downconverter and Sonnet. Now, am I allowed to go on for another 5? Okay.
Yes, you have still 5 minutes.
Right. I just wanted to add in an appendix to this because I mentioned I might talk about it yesterday. And a few people asked questions about this Sonnet program. As I said yesterday, it's a full electromagnetic simulator, so it allows you to take a structure such as a line or a filter or pin through the board and actually analyze what this is going to do. And it's practically as good as building it. You can play with the design, you can lengthen lines, change the spacing, and it's almost like making them. And it's quite a lot quicker than making them. I'm getting, with these filters, probably about 20 megahertz accuracy of prediction of the resonant frequency between the program and what you measure, which is within the bandwidth of the filter. And they always come out so that you can cut the line off slightly to bring it onto frequency rather than have to add metal. So it seems to err on the wrong side. That may be the way I'm using it. But it's been very useful for designing these kind of filters, as we talked about yesterday, amplifier matching circuits, and also branched arm couplers, which if you use conventional so-called closed form simulators where they've got equations to describe junctions of lines and so on, those are just equations and they have limitations as to accuracy. And you very often find your 3 dB coupler has got usually the phase comes out very well, but often you get quite bad amplitude imbalance between the two outputs if you just use this kind of, the other Quux or software like that, AWR even, they're not very good for designing a first-pass success with a 3 dB coupler. But this thing will get them smack on. You just build it, and then it's up to how accurately you can etch the lines, and the things just work. I've done several of those now. So this is the tunable filter from which you saw before from the Downconverter. And that's the 3D view, as they say. The 2D view is that. And these are basically, you just draw rectangles. The software's got a fairly crude, but if anyone's ever used AutoCAD, it's very much the same user interface. To draw rectangles, join them together. You can check that the lines are actually connected, because if you leave a little, 0.001 millimeter gap between the metal, then the software will analyze it fine. It just looks terrible because it's not connected. So you can check for errors like that. You can highlight blocks, move them around. For example, in this one, you could click on that block and move them together, if you like, to investigate the tapping point and try and optimize it by hand for best match. And you can highlight, so the top of the lines and move all those together to change the frequency. So it's quite easy to use once you've got the hang of it. You have to set up the dielectric constant of the board, the thickness, and all of these things, but it's all relatively easy to do. It will also allow you to connect netlists, which is where circuit elements are connected by numbers. So that previous thing here has got 6 ports. It's got an input 1, 2, and then up here 3, 4, 5, and 6 around the gaps. So this generates a matrix of numbers, a so-called 6-port network, that you can then stick in this format. So that says S6P is a 6-port network connected between nodes 1, 2, 3, 4, 5, 6, and it's something that you've already run in Sonnet before. So it's outputted an S parameter file. And in this case, I've just connected 2 varicaps into those gaps using this. So the BB8333S is parameters that you've got off the web for the varicap at all the different voltages. And that will allow you to do nice predictions of the frequency response. So this is with 3 volts tuning. This is 0 volts tuning. And you see varicaps when they have no voltage on are quite resistive. Or should we say the impedance is dominated by the resistive part of the diode. So the filter loss is nearly 5 dB when the tuning voltage is 0. But by the time you've got the tuning voltage up to +3, it's moved the resonant frequency up a bit, but the loss is now much lower. And this is what you see in reality. So the software is predicting quite well what you see. Thank you very much for your time, and hope to see you on 13, wherever you are in the band.
Thank you very much.